Hi there, this is the fifth video of Work Energy Methods, and in this video I'm going to be discussing a similar situation as the previous, except this one will include a spring in the problem. So what we're going to have is, first off, let's just describe three different situations. One is a ball that's sitting, let's say, 2 meters off the ground or something, and you have the spring. This will be named our situation 1. Okay, so that's situation 1. Our situation 2 is going to be the ball is right here just before it begins to compress the said spring. Excuse my drawing. So no contact yet. No contact yet. And this is going to be situation 2. And then let's split it up one last time. And this will be when the spring is actually really just compressed by the ball. So what we have is we have three different situations. Let me label this last one as 3. And we have 3 different situations, okay? The first one is the ball is stationary. So I'm going to say that V naught is equal to, or V1 I should say, is equal to 0. The potential energy is such that you're up 2 meters and the spring is obviously not acting on the ball at this moment. So mostly all you're going to have is a potential energy situation right here. This is potential energy. Okay, so then we go to situation 2, where in situation 2 you're going to have a height of, let's just say, if we were to measure it from the bottom of the ball, it's 1 meter, assuming that we did the same on this other one, let's say. If we were to measure the bottom of the ball, you'd realize that you'd have a potential energy still of 1 meter to the ground. However, this spring is still not acting on the ball, so no spring. However, there is a velocity at some point, so we need to find out what V is going to equal. 2 equals what? We need to find that out. And also, it'd be nice, you can use the potential energy and the previous solution of the previous situation to get that V. And then finally, in this situation 3 here, this in red, you're going to have, once again, V3 will equal 0 because the spring will now be taking all that. You're going to have an interesting potential energy because it will be a combination of such. The height is no longer going to be 1, it'll be 1 minus whatever the compression is, whatever x is. So if x were to be based off of the original height going down, then this amount right here be x. So that's just the amount the spring is being compressed. That's your x. So if we were to describe what the potential energy is here, it's going to involve both the spring potential energy. That's how we're going to describe our energy here. And just to kind of backtrack and show in this situation what it's going to include, this is just going to be the kinetic energy plus the potential energy. Realize that all these situations are going to be interrelated because no energy loss will be due to friction or anything of the sort. Okay, so let's just jump right in. Jumping right into the first situation, we know that in this situation that velocity is 0, so kinetic energy is not going to affect since there's no movement. And we know the spring is not being compressed, so the spring is not going to add any energy into this. So potential energy is all we need to worry about for situation 1. So let's just solve for potential energy. Situation 1. Since potential energy equals mgh, it's fairly simple to say that if the mass of the ball, which I don't think we've done that yet, but let's just make an assumption of 1 kilogram mass. So mass is equal to 1 kilogram. So anyway, with that assumption in, you can run with some of these numbers. 1 times g, 9.81, times height, which is going to be 2 meters. And that'll be added up, and you'll calculate that out using your algebra, 19.62. Now, just recognize this as our energy units, and let's just run right into situation 2, where basically kinetic energy and potential energy will be included. Realize that the height is going to be 1 meter instead of 2 as it was in the previous situation. So, running with this, situation 2, you're going to have your PE portion, potential energy portion, still to be MGH, which will be 1 still and 9.81. Still going to be our gravity, but H is no longer going to be 2, it's going to be 9.81. This is the potential energy portion. That means that the remainder, the subtraction of these two, since there's not going to be any loss, we know that the potential energy of situation 1 is going to equal potential energy plus kinetic energy. So thus, if we were to just subtract this over, then we could find out what the kinetic energy is and backtrack and find out what our velocity is. So if we do that, we find that 9.81 is a result of the PE2 minus PE1 equals 9.81, which will equal 1/2. It will equal kinetic energy of 2, which is going to equal 1/2 m, which is 1, v squared, which if you just let me solve for it, v is equal to 4.43. Not too complex. You just got to be aware of what's going on in the situation. Now, realize that we can, rather than carrying over this solution, we can always look back at our initial solution of 19.62 as the total energy in the system, because we know that there's going to be a conservation of energy. So knowing this, we can actually slide right on into situation 3, which we know will equal 19.62, is going to equal both the potential and the kinetic energy. Now, one thing to note here in situation 3 is that the height is no longer 1 foot or 1 meter. It's going to be, the height is going to equal 1 minus x. That's going to be our height. So that's what we need to remember for potential energy. And the spring is going to equal 1/2 spring energy is equal to 1/2 kx squared. A little bit different, but looks very similar to some of the other ones. So if we were to actually toss this in, our solution is equal to potential energy plus the spring energy. So potential energy is going to be mgh, or 1, 9.81, and h, which is going to be 1 minus x, plus 1/2, and then k, which we didn't assign a k, so I'm just going to say 2 kilonewtons per meter, which will be nice. That'll round things nicely off. Let's say if k was equal to 2 kilonewtons, which I'll just put on here, k is equal to 2 kilonewtons a meter. If that's true, back to red, then this will equal 2,000, just to bring the units back out, x squared. Now realize that we have this big long equation and one unknown. That means that we can solve for this. We should be able to solve this and get this equation. 0 equals 1,000 x squared minus 9.81x minus 9.81, which when you use the quadratic equation or the quadratic formula, You can solve for x, and just to give you an answer, x is equal to 0.104007 meters. So what that's saying is that this is only going to travel 10 centimeters. It's only going to compress that spring just over 10.4 centimeters of compression before this thing stops. And so that's how you can gauge what type of spring you want or where you're going to put it. Anyway, I hope this was useful to you. I know that it gets a little bit complicated when you start talking about 3 different situations, but you'll find out that this will save you a lot of time rather than trying to use other numerical methods and such. So anyway, leave any comments if you have any questions, and I hope you have a nice day.